तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last class, we were looking at incompressibility. Before that, there was a question on what we mean by dot, say sigma dot, epsilon dot, or lambda dot, what this dot really means. There was a small confusion. I had said that, said this before, and I am just repeating that. We are not into what is called as rate dependent phenomena when we talk about plasticity. These rates are pseudo rates. So, sigma dot is perfectly equivalent to writing delta sigma. Both of them are the same. Okay? That is, in other words, delta sigma when divided just by delta t. What is this time? Time has nothing to do with your application of load or loading time or whatever it is. It has nothing to do with that. Just it's a pseudo time to only capture that the loading has to be applied in an incremental fashion. That's all. Okay. So, this lambda dot, sigma dot, epsilon dot in one sense convey that the approach is incremental in nature. Okay. But we are going to see there are some other things that come into picture later in the course, but right now you can say that sigma dot and delta sigma, they are both of them are equal. Okay. So, the loading carries itself in time. So, in one sense the rate of loading is what is manifests as or comes out as sigma dot and so on. Okay. But this rate of loading does not mean that we are taking into account the inertial effects or rate dependent effects or strain rate effects and so on. Okay. Once you are looking at strain rate effects, then the time should be the correct time, it can't be a pseudo time. Is that clear? Okay. We will give more explanation to it as we go along in the course, but let us now look at a very important thing called incompressibility. Now, what is incompressibility? There was a question again in the last class when we finished that what is incompressibility? Incompressibility simply means that there is no volume change. Incompressibility does not mean that we can't compress it, we can compress it, but when you compress it, the compressive strains that are developed are such a fashion that there is no change in volume. Is that clear? That is what it means. Now, we know that when it is compressible, we will prove it again in a more rigorous setting later in the course, that when incompressibility is a condition, then mu is equal to 0.5. Now, let us look at the difficulties that happen, that take place when we have mu is equal to 0.5. Since this is a material behavior, the culprit is going to be a D matrix. All of you know that this is the elastic matrix. Now, let us split this D matrix into a part which is going to be my problem or problematic part, and a part which is not going to be so very problematic part. So, in order to do that, let me define the shear modulus mu or G to be E divided by 2 into 1 minus nu, and the bulk modulus B to be E divided by 3 into 1 minus 2 nu, and say that this D now can be split into two parts. One which goes along with the shear modulus, the other part which goes along with the bulk modulus. Let us see how we can split this d. This is regular d, we are not talking about dt now, just we are going to look at regular d. Now this d can now be written as, say for example, g into 4 by 3 minus 2 by 3 minus 2 by 3 0 0 0 minus 2 by 3 4 by 3 minus 2 by 3 0 0 0 and so on as one part, plus the other part consists of b into, b is my bulk modulus, into and so on. Of course, the last rows are zeros. Then this becomes 0, 0. Yeah, this part, this is 0. This is no, third is minus 2 by 3. Okay, minus 2 by 3, 0, 0, 0, 0. The rest of 0, 4 by 3, or sorry, 1, 1, 1, and so.
6 by 6 matrix.
Yeah, this is 6 by 6 matrix. This is a 6 by 6 matrix, which, of course, we are talking about. This is the relationship between sigma is equal to d epsilon. So we are splitting this d into two parts. So what goes into B transpose dB? Now, if you look at these two parts, the culprit obviously is here, because you have 1 minus 2 nu term here. Okay. So now substituting, let me call this as, say, ds, first part as ds and second part say as dB, to indicate that one part is formed by shear modulus, the other part formed by bulk modulus, so that my total k consists of B transpose. Instead of d, I am going to say that d shear modulus and bulk modulus, B d omega. This is ds and dB is what I am going to write ds. So I have two terms now in k. So let me call that then B transpose ds B d omega plus B transpose dB B d omega. Now, so in other words, my k can be split into two parts, say ks plus kb. Is it clear? Of course, ts is complete thing. So okay, so you can, this b goes here. Okay, you have a b here. I mean, of course, it goes into dB. What happens when we get nu is equal to 0.5? B goes to infinity.
The same with D, G. TS also had.
No, please note that in G I have only nu. So when nu is equal to 0.5, this G does not go to infinity. But when I have B, which is there in this KB, okay, second part, where I have a B, then you will see that E minus 1 minus 2 nu is equal to 0.5, so this goes to infinity. So as I approach nu to be 0.5, all my troubles start. Even at 0.49 or 95, 499 and so on, this will make this K matrix, the situation will make the K matrix to be highly ill conditioned. And inverse here of this matrix is going to be difficult, because once it becomes ill conditioned, okay, that means that it is going to a situation where it's almost, infinity, then I will have problems. At 0.5 completely incompressible, then it's totally out. Maybe you can work up to 0.45, 44, it may not be a problem. Now what do I do? What do I do to alleviate this problem? In a crude sense, I mean this is not, I'm not going to talk total theory, we will come to that a bit later. In a crude sense, you may think that there is a solution. What's the solution? The solution comes from a possible mistake I may make, use the integration rule. Probably you would have remember or studied what is called as rank deficiency or hourglassing. In our earlier class, we said that there is a particular integration rule I have to use in order that I can integrate this accurately. Polynomial of 2n minus 1 integrated accurately with an order of n. Okay. Now, so in other words, we said that for a quadrilateral, I have to use a 2 by 2 integration. What happens when I reduce this integration, when I go to 1 by 1 rule? I will get into what is called as rank deficiency. Okay, what is called as hourglassing. Okay, the rank of the matrix is not sufficient enough for me to invert and make it stable. Okay, I'll get into singularity problems and so on. So there is what is called rank deficiency when I reduce the numerical integration, and so I avoided it. So I will go for full integration. If at all I do reduced integration, I do other procedures called stabilization procedures. Okay, so that is called as hourglassing, and in order to avoid hourglassing, I did some what is called a stabilization procedures, or in other words, you call this as hourglass control. In fact, if you had used many of the explicit finite element code, you would see that most of them use a reduced integration and they will have a proper hourglass control. So in other words, by making a small, if I may call it a mistake within quotes, okay, I got into some trouble and I got out also by doing some damage exercises. So the major thing is that matrix was becoming singular when I did those things. Now what I am going to do now is very similar thing. I am going to make the mistake wantonly. How am I going to do that? So having known that this kind of problems will exist, what I will do is simply take this, okay, and perform an under integration or reduced integration. So in other words, I selectively integrate a part of the K matrix in a reduced fashion. So instead of 2 by 2, I may use 1 by 1 rule. If I need 3 by 3, I'll use 2 by 2 rule. Now I can reduce the integration, order of integration. So once I make that decision, my problem to a great extent is solved, because this KB matrix will become now singular. Okay, this will not have, so this the whole, though I will still have K from here. Okay, so this contribution, this problem of inverting this and going to infinity will not happen. Okay, so that is called as selective reduced integration. So this problem of inverting this, I will not have difficulty. I have difficulty in the sense that that would automatically be taken care of by reduced integration. Now this looks like a crime. Okay, people call this as crimes and so on. Variational crimes, a common word that is used many times. Okay, this looks like a crime, but But a beautiful paper by Simo and Hughes showed that after all what you are doing is very well within the framework of variational approach. So though it looks as if we can do the whole thing by learning from a mistake, okay, it interestingly has a very good theoretical background as well. It comes from some of the variational principles which you might not have heard, and we will see that in this course. So by doing this selective reduced integration, okay, I can in one word alleviate many of the problems. Is that clear?
How to map the order? Because
How do you find out the order? Yeah, but you know the full order of integration that is required. This depends upon the powers or the polynomials that are there. Okay, so that is why I said 2n minus 1 polynomial is integrated exactly by n-point integration rule. So depending upon what is that you have, you can find out the exact, and then you can reduce it accordingly. Okay. Now this is fine as far as this kind of simple elastic problems are concerned. Okay, and the approach seems to be sort of, though not very correct, looks logical. Right. Now how do we do a problem like plasticity or some other aspect where, okay, I can't write this very clearly like ds and db and so on. Now various methods have been proposed, and one of the methods which is very popular is called as a BBAR method of Hughes. We will see more theory after we do this. Okay, we are going to do the same selective reduced integration, extend this concept what we have given here. Okay, I have not introduced, there is a lot more again simple things that you can talk about this. You will see that this b here works like a penalty constant, but since we have not done a lot more on penalty approach and all this, I am not commenting on that, but suffice it for me to take me to the next group of algorithms which come under what are called as BBAR method. What essentially BBAR method does is to now alter not this d but to alter b. After all, you can see that the culprit seems to be in the volumetric part, and so can I now split b into two parts, a deviatoric part and a volumetric part, and do something to the volumetric part, okay, of k which results from splitting this b, okay, that b volume. Let's proceed instead of t splitting b. Okay. Yes, this, what is this b, correct? The b is the strain displacement relationship. Okay, b is the strain displacement relationship, which is epsilon. In this case, epsilon happens to be b into the degrees of freedom. Okay, degrees of freedom, which you can call this as u hat. Now there is a difference between u and u hat. Okay, note this subtle difference between them. U is the displacement of a continuum. Now I'm going to use this because I need some other leeway to define these two separately. So u is a displacement of a continuum. In other words, u is a vector which can be written as, say, this u is ux comma y and vx comma y. This u hat is the u at the, say, nodal locations, right? It's at the nodal locations. So suppose I have 1, 2, 3, 4, then u1, u2, v1, u1, u2, u3, u4, v1, v2, v3, u4, that come under u hat. So b is of course the strain displacement matrix. See, this is the continuum u, right? This u and v are the continuum u. this u hat is after this continuum is discretized, and you suppose I call this as 1, 2, 3 and 4, then u hat gives me a vector of the form say u1 v1 u2 sorry v2 and so on up to u4 v4. Okay, this vector is what I call by this u hat.
Before that, earlier we used to use it without hat.
Yeah, without hat, yes, that is because in the next formulation I am going to use certain things with u as well, so that is why we are looking at this more closely. As you raise your level of understanding, you have to distinguish between u and u hat. In other words, continuum u and discretized u. Say maybe in our earlier classes we had put this as bu, okay, and understood that this u is this. We never worried about the continuum u. Okay, sometimes it may be necessary to have that also. Okay, so that strain epsilon we will define that as su. S is my operator. Okay, we will define that again a bit later. Okay, so let's now define it like this. Okay, now of course B is a matrix. B is a matrix which consists of say B1, B2, B3 and so on up to B into number of elements. So suppose this is what is it? You know, what is the size? So this is say 6 by 1, and this happens to be, is it 6 by 1?
8 by 1 for
Yes, for we are talking about this quad 8 by 1, and so 6 by 8. Okay, is that clear? So this B matrix as a submatrix as well, okay, with 2 in each can be written as B1. B1 is itself is a submatrix, 0, 0, 0, say B2, 0, 0, 0, B3, all of them are matrices, 0, B2 or B1, B2, so depending upon whether you write epsilon 2 3 or epsilon 1 3, and then B3 0 B1 and B2 B1 B3 B2 or B3 yeah B2 B3. Let's check that out. So suppose I have epsilon 1 1, this will become, so that should be B1 0, sorry, it should be B1 B2, yes, just we will stick on to the same thing, do you sorry B2 B1, B2 B1 0, B3 B2 B3 B1. So let's put it like this. Anyway, you know what these B's are. Now what we are going to do essentially is to split this B into two parts, okay, a dilatational part and a deviatoric part. Let me call this B dilatational part to be say 1/3 of, this comes out very easily, B1, Okay, B1 comes from that, this one, B1, B2, B3, B1, B2, B3, B1, B2, B3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Now, how did I get that? 1 minute. How did I get that? I got this from the fact that the dilatational part is given by epsilon 11 plus epsilon 22 plus epsilon 33, okay, and similar to what we did for pressure by 3. So epsilon 11, 22, 33 consists of sum of B1 and corresponding to U1, okay, B2 corresponding to U2, B3 corresponding to U3. So B1, B2, B3, okay, together forms epsilon 11, 22, 33, right? So that is why we had that by 3, and so that gives the dilatational part. This B. Yeah, let's, okay. That was covered in the last class or last course, but it is quite simple. How did we get epsilon? You know, just look at how we derived epsilon. So epsilon, say epsilon 11. What is epsilon 11? Dou u, yeah, dou u by dou x. So in other words, dou u by dou x1. Okay, if you want to keep u as u1, u2, u3, and so on, so you will say that dou u1 by dou x1. Okay, epsilon 22 dou u2 by dou x2, and so on. So what is epsilon 12? Half of u I comma j plus u j comma I. Okay, dou u1 by dou x2 plus dou u2 by dou x1, right? And similarly you can write. Usually, like I said in the last course, we will not use epsilon. Most of the time you will use only gamma 12, the engineering shear strain, right? Yeah, 1 by 2 will not be there. That's why we have removed that, right? So this actually can be written in a matrix form. Let me remove this. We'll come back to this in a minute. We were repeating some other things. This can be written in a matrix form as epsilon is equal to u with first entry being dou by, say, dou x1. Suppose I am only looking at a 2-dimensional case. You can extend it very easily to 3-dimensional case. So that, let me see, that is epsilon 11, next is epsilon 22, say gamma 12. Only these 3 I'm going to see. Okay, then this can be written as dou by dou x1 0, 0, 0 dou by dou x2 0. Okay, then I have to multiply. So first one will be dou by dou x2, dou by dou x1 0. Okay, this would be the for these 3. So I will have actually, because 3 3 was not there, this was all 0. In other words, you can look at it even as just like that. So of course, when I want to have a complete set, then I may have to extend this into 3 rows, or rather 3 columns and 6 rows. Okay. So this matrix is what I would call as a S matrix. Note that this U is my continuum U. This is what now is replaced by N into discretized U. That is what I called as U hat. So S into N into U. right? Okay. Now let's not worry about the isoparametric. N is our shape functions, obviously. So u hat, this is what is called as my u hat and nu. So now this multiplied by this Sn. Okay, so this can be written as Snu. So this Sn is what is called as u hat. That's u hat. So Sn is what is called as b into u hat. So you can write down b very easily. Is that clear? Yes. This is for one u. So if I now put down all the nodes, correspondingly I will have in u, I will have corresponding to all the nodes. So I will have u1. So let me call this as from u1 to u8 to make things clear again. So u1, u2, u3, u4, u5, u6, u7 and u8. Okay. So u will be defined in terms of n1, n2, n3, n4. So how do you write n now? N will be 3. See, this will be, say, let us come back to dimensions of this. So suppose I am looking at 6. So 6 here, so 6 by 1, okay, is equal to S will be 3, 6 by 3. What will be n? N will be 3 by 8. Sorry. And u will be 8 by 1. So that 6 by 3 into 3 by 8, 6 by 8 into 8 by 1. Now my B matrix I said is 6 by 8. Okay. So that is what I wrote this as in a form which is, combining this, I wrote it like that, B1, B2. So that's why I said B1 is a submatrix. Is that clear? Okay. So symbolically, I mean, I'm not expanding all this. So symbolically, I'm writing it so that you will, hereafter I won't write u1, u2. I will just say that this is the u vector. That's all. Okay. Fine. So please note that the number of degrees of freedom also entered into this B matrix. Right. So this B matrix is the one which I say can be split up into two parts. Okay. One is B dilatational part plus B deviatoric part. B dilatational part and B deviatoric part. The dilatational part consists of 1/3 of B's. Okay, 1/3 of, say, the first part of B is or in other words, the dilatational part comes from the fact that it is epsilon 1 1 plus 2 2 plus 3 3. Okay, so I can write this as B1 B2 B3. It's the same B1 B2 B3 B1 B2 B3. This is for actually what we did here. Note that this is for 2D case. Okay, if I have to, actually this is a small, I think we didn't do this correctly. Sorry, 1 minute. We didn't do that correctly because we are looking at 3D case. So 3D case is, actually we extended it to 3D case. So in 3D case this is equal to 6 by 1 and yes is, there are how many rows? 3. So how many columns? 3 columns and 6 rows. So 6 into 3. Okay. Then here it is 3 into, say for example you are looking at a brick element now. Brick element 8. 8 into, yes, 8 into 2, number of degrees of freedom, 16. So this should be 3 into 16. So 16 into 1. Which one? Yeah, 8 into 3, 24. Yeah, not 62, not 2, 3. So 3 into 24 and 24 into 1. 24 into 1. Correct. So 6 into 3 into 3 into 24, 24 into 1. So that now B matrix is actually S into N, which means 6 into 24. Into 24. And so each of these B1 are 8s. Yeah. So that is why now B dilatational 1/3 is written as B1, B2, B3. These are matrices. Now you know what they are. B1, B2, B3, B1, B2, B3, 0, 0, 0, 0, 0, 0, 0, 0, 0. Right? 1/3. Yes, wait a minute. Let me finish it. So plus I have a deviatoric part such that the sum of this deviatoric plus dilatational part will give me B. Is that clear?
How we came to this one, sir?
No, I am splitting this B into a dilatational part in the same fashion that I can split strains, because after all these are strain displacement relationship. So in the same fashion I can split strain. I am splitting B into the dilatational part and deviatoric part. Right. So the dilatational part is this and deviatoric part is the other one. So in fact, if I am going to write down these two before we write down the equation and substitute this into my K matrix, you will see that I can write that down as my K matrix or KT matrix. It can be written as integral omega, say B deviatoric, please, plus B dilatational. I am going to introduce a lot more theory, but quick glance of what we are going to do. Transpose D, okay, into same way B is again split, B deviatoric plus B dilatational, or dt into d omega. So wherever I get the dilatational part, okay, I am going to under-integrate, okay, and deviatoric part is full integration. So in other words, this B1, B2, what you see here, will be replaced by a new B's called B bars, which is the result of under integration. There are various ways of getting B bars. We will see that in the next class. Okay, one is by under integration, and you will see that we can get the same formulation by going over to another formulation called mixed formulation. Okay, it is possible to go to a formulation called mixed formulation. I'll just explain it in a minute and come back to this again. But I just want to say here that now I'm splitting B. The essence of the story is that I'm splitting B, I'm splitting this into a deviatoric part and a dilatational part, and I am concentrating on the dilatational part and under integrating it, and the deviatoric part, okay, I am doing full integration. So in other words, if I just look at the implementation, what will happen is that in an element I will have 1, 2, 3, 4, 4 Gauss points, okay, for a 2D element, correspondingly 2 by 2 by 2, the 3D element for not a, no, it's not a higher order element, just 4 noded element, okay, and these 4 nodes or 4 Gauss point rather are used to integrate the deviatoric part, and I will use one Gauss point at the center to integrate the dilatational part. Okay, so this is called as selective reduced integration. Yes. Yeah, usually you don't consider them, but you take that separately as deviatoric dt. That's why we will call that as a BBAR. You will see how it comes up in the next part of the derivation, the mixed formulation. But you will usually you take deviatoric part separately into dt, okay, dilatational part separately. So you will have deviatoric dt, deviatoric, dilatational dt, dilatational. Okay, these are the two things that you will take them up separately. In other words, it's not very correct to split that. In fact, I should have written this as B consisting of, actually this comes from my P matrix from the B transpose sigma. Actually, I shouldn't have written it like this. Actually, we should have written it as B transpose sigma d omega, and from here I should have written this as B deviatoric plus B dilatational sigma d omega and so on. Now, so in other words, you will have only two parts, B deviatoric, D B deviatoric plus dilatational part. So that is what you under integrate. So you will have, actually if you really look at it, you will have 5 Gauss points. These 4 are the ones which are used for deviatoric part, and the center Gauss point is what is used for the dilatational part. Okay, so you will have, so in other words, the history variables are stored in all these 5 Gauss points as well. Okay, now what is the theoretical background? We will do that the next class to this. The theoretical background for this comes from what is called as mixed formulation, and going over to a variational approach called as Hu-Washizu variational principle. In the mixed formulation, you have, instead of displacement alone as a variable, you also have sometimes P as well as the volumetric strain epsilon v. So when I have U, P and V, epsilon v as a variable, then we call this as, there are 3 things. So these are, you have 3 mixed formulations, or sometimes you will have only, okay, U and stress. Okay, these are 2-point mixed formulation. We will talk about mixed formulation and Hu-Washizu rule or for variational formulation in the next class, and tie that up and go into the details of this B, okay, and how that comes about from Hu-Washizu principle in the next class. Okay.
We can't be in plasticity problems. Why can't we decompose D into deviatoric? What is the problem?
Yes, because in the plasticity problem, can we decompose dt clearly? It is not possible as simple as what we did for an elastic case, okay, because elastic case we had the shear modulus and the bulk modulus clearly defined and quite easy to demarcate it. We will have problems when we do that, okay, in the plasticity part of it. Okay. So let us look at the mixed formulation and then talk about the rest of it.